All right, 13, part 3, we want to talk about the induced voltage. And basically what we're going to say is the induced voltage, the induced electromotive force, is minus the change in the flux over the change in time, how long it takes to change that flux. So we talked about the change in flux last time. We just said that the change in flux could come from the change in area or a change in magnetic field. We did a little example where we changed the flux by tilting the loop. And now we'll talk about this. Well, this is actually all we need to do. So this is how we're going to start with interactions between the electric and magnetic field. And you're saying, I don't see electric or magnetic fields here. But remember, phi is equal to B perpendicular A. So that's our magnetic field. And E is related to the field. So the electromotive force, or the voltage, is related to the electric field times the length. Or we could look at it as the electric field is equal to the electromotive force over a distance. In either case, what we've done is we've now got two things, these guys, that we're more or less setting equal. There's a delta T in there. That relates the magnetic field and the electric field, although it's only a component of the magnetic field, that's true. But it's still a part of the magnetic field is going to change and create an electric field, right? And that is related to geometrical factors. This is just, this is just the length over the thing that we're talking about, and this is just the area of a loop, right? So get rid of these guys because of the equal signs, and we basically have the magnetic field and the change in the magnetic field doing something to the electric field. All right, so that's more or less where we are here. That's all I have to actually say is that the induced EMF comes from a changing magnetic field. All right. And that's more or less Faraday's law. This is the closest thing to a fundamental law of physics that we're going to look at here in this class. Faraday's law there, which is one of the three Maxwell's equations. The other two, Gauss's law and Ampere's law, which are actually very important for electrostatics and magnetostatics, but they're kind of complicated mathematically, or too complicated for this class mathematically. They were only seen in circuits, which was, one was the junction rule, Gauss's law, and one was the loop rule, Ampere's law, for circuit networks. So this is the only one that we actually use in a reasonably close form to what it is. So those are basically three of the four Maxwell's equations. The other Maxwell equation that you're not going to get to play with is the law with no name. It's basically an equation that says there are no magnetic monopoles in the universe. We talked about that a while back. So I guess we have looked at all four, right? So I hope that's enough. So after I do an example here where we'll talk about putting a current through something and find out what the induced current is using the EMF, we'll go on to the next lecture. All right? Bye now.